All right, here we go. So this is Unit 6, Part 1. I think we're going to do this in 3 parts, some of which are meant to help you on the way and help you understand the learning objectives for this unit. Now we're talking about inferential statistics. So up until this point, we've been comparing means or doing cross tabulations, but we haven't talked about what this means for the general population. Our means, we've come up with mean values of y, and we've called them y bar. That is the value of y in the sample population. The question is how much does that translate onto the value of y in the actual population in the rest of the world? So what can we conclude from this? What does that mean about this, which is the real value of the mean of y in the real world? So what we're talking about here are tests of significance, and here we're going to be talking about testing the significance of a zero-order relationship and how we do that. So we'll use our first example. Our first example is dog ownership and whether or not that predicts feelings towards Barack Obama. And so we have our hypothesis. Our hypothesis is this, or another way of saying is that we have a hypothesis that X has an effect on Y. And of course we found out that it turns out it has a negative effect, but really our hypothesis is sort of agnostic in some ways at its most basic level. It doesn't really care about directionality. The hypothesis is simply, H1 is simply X has an effect on Y. What we want to do is reject the null hypothesis, we'll call that H0, that X has no effect on Y. We want to try to see if we can demonstrate the fact or disprove the idea that X has no effect, and we'll talk about that a little bit more in a second. So again, our hypothesis here is that in a comparison of individuals, those who are dog owners are more likely to have warm feelings towards Barack Obama than those who don't own dogs. Of course, the opposite is true, or at least appears to be, and we're going to find out just how true. So you'll recall this from the last unit. This was our means comparison table, and what we discovered was that as you move X from no to yes, if you move X from 0 to 1, the value of y bar, our predicted value of y, changes by about 10 percentage points, 9.5 percentage points, something like that. So it appears that X has an effect on y of about 9.5 percentage points. I guess maybe it was Unit 3 we worked on this before. But the question for us is does that effect exist? Right? It appears that X has effect on Y. And that's within our sample of 1,931 people, 1,931 respondents in the United States of America. But does that effect hold throughout the rest of the country? Can we confirm the idea, or can we rest assured in the idea that even though that appears in our sample, does it appear in the rest of the world? And as we discussed in class, the way to do that is to use standard errors to predict a confidence interval about each of these values. So right, when we're talking about a confidence, like how confident are we about the upper limit of the confidence interval, and how confident are we about the lower limit, and how far does that go out? So what we're going to do is predict something called a standard error, and that is our best estimate of the amount of random error in some way. It's a measure of the amount of random error based on variance and size of sample. And again, we'll talk about that more in class. We'll probably already have, I hope. So what we're trying to do is find a confidence interval, again, about this value. And the way we do that is by finding a standard error and then moving two standard errors away from this value and from this value. So we have a standard error. That standard error is determined by taking the standard deviation and dividing by the square root of n. By taking the standard deviation of y bar and dividing by the square root of n. And when you do that, you get this value here, this standard error, and this standard error. The way to predict then the confidence interval is again to move two standard errors away from either direction. So what I can say is that when I do that, so if I go 2 standard errors below 65.34, I get something that looks like 63.34, which makes a lot of sense. If the standard error is about 1, right, which is what that appears to be, and I move 2 standard errors away, I would basically be subtracting 2 from 65.34, and I get 63.34. And if I move 2 standard errors up, I get a value of 67.34. And that makes, again, a lot of sense given the nice sort of, this is about more or less 1. So you can imagine that 65, the mean of y bar, is right here in the middle of this at 65.34. And we've moved away 2 standard errors up to 67.34 and 2 standard errors down 63.34. So I'm 95% sure that the real value of y, that y hat, is somewhere between 67.34 and 63.34. Similarly, I can do the same thing. I can take the standard deviation divided by the square root of n and predict the standard error of y bar when x is equal to yes, or say when x is equal to 1. And that gives me, again, a standard error about, and if I move 2 standard errors away, I can be 95% sure about a range of values for y bar when x is equal to yes. And so in this instance, right, we had 55.74 and a slightly larger standard error. There was more variance. So when we move 2 standards away, I get 53.36. That's about 2 below 55.74. And 2 standard errors above is a little bit more than 2 percentage points or 2 feeling thermometer points above. And that's a pretty narrow confidence level interval, all things being equal. So again, I'm 95% sure the true value in the true world amongst people who do own dogs is, at least, or was in 2012, somewhere between 53.6 and 57.8. And what that tells me then, right, what we want to say is, okay, so we have basically, we're 95% sure that the true value in the true world is somewhere between here and here, and the true value when x equals yes is between this point and this point. And what you'll notice is that these 2 intervals don't share any values in common. One ranges between 53 and 57. This one ranges between 63 and 67. And what this means is I can reject the null hypothesis with 95% confidence. I can say, look, I'm 95% sure, or better, I'm pretty confident we could move out 3, in fact, I'm sure of it, we could move out 3 standard errors, but we can talk about that later. But I can, if I move out 2 standard errors from either one of these values, the intervals that result do not overlap, right? The upper boundary of this one, which we put at 57.84, is substantially less, and it doesn't even have to be substantially less, it just can be any amount less, than the lower boundary of 65.3 of the people in the know. So I can say that these 2 values are distinct from one another, which means that, or at least I'm 95% sure that they're distinct from one another, and that means that I can reject the null hypothesis with 95% confidence, and that, of course, is our goal. I am 95% sure, or 95% confident, rejecting the null hypothesis. And the null hypothesis, of course, was that x had no effect on y. I'm 95% confident, saying, in a way, is another way of saying I'm 95% confident that x has an effect on y. And if these intervals overlapped, I wouldn't be able to do that. There would be a chance that these 2 values could be the same value, but in this instance, they can't be, and I'm 95% sure of that.